Today's topic is TTL characteristics. We will discuss different characteristics of TTL circuits. 7400 series devices are guaranteed to work reliably over a temperature range of 0 to 70 degrees centigrade and over a supply range of 4.75 to 5.25 volt. So TTL devices can work reliably over this temperature range 0 to 70 degrees centigrade, and range of supply voltage is from 4.75 volt to 5.25 volt. It is 0.25 greater or less than 5 volt. Worst case means that the parameters like maximum input current, minimum output voltage, and so on, these parameters are measured under the worst conditions of temperature and voltage. We have different parameters, and worst case means these parameters are measured under the worst conditions of temperature and voltage. Floating inputs. When a TTL input is low or grounded, a current IE exists in the ammeter as shown in figure A. In this figure, ammeter of the transistor is grounded, so ammeter current flows in this direction. Ammeter current flows in the direction of arrow, and it flows in this direction when ammeter is grounded or given 0 volt. On the other hand, when a TTL input is high, that is in figure B, this ammeter, at this ammeter we have applied voltage plus 5 volt. In this case, the ammeter diode cuts off and the ammeter current is approximately 0. Current through the ammeter will flows only when this ammeter diode is in forward bias condition. In first case, this is in forward bias condition when ammeter is connected to ground. So a maximum current IE flows in this direction. When ammeter is connected to plus 5 volt, it is in reverse bias condition and approximately 0 current flows through it. When a TTL input is floating input means it is not connected, it is unconnected as shown in figure C. In this figure C, this ammeter is not connected neither ground nor plus 5 volt. It is open. When this ammeter is open, we called this input as floating input. No ammeter current is possible. In this case, no ammeter current is possible. Therefore, a floating TTL input is equivalent to high input, because when input is high, no current flows through this ammeter, and when input is disconnected or open, or we say it is floating input, then also there is no ammeter current. So this floating input of figure C is equivalent to this input, high input, that is plus 5 volt. Figure C produces the same output as that of figure B. So in building circuits, any floating TTL input will act like a high input. In figure D, the input is floating and is equivalent to high input, so the output of the inverter is low. In this figure, this is the inverter, that is NOT gate. If input is open or floating input, output it behaves like high input, so output of the inverter will be low. Worst case input voltages. This figure 1 shows a TTL inverter. It is same as standard TTL NAND gate. Only difference is that in this circuit, in transistor Q1 there is only one ammeter, and in standard TTL NAND gate, in this transistor Q1 we have multiple ammeters. If we want 2 input NAND gate, we have 2 ammeters. If we want 3 input NAND gate, we have 3 ammeters in this transistor Q1. But if in this transistor Q1 there is only one ammeter, then this circuit will behave like a NOT gate. If input is high, output VO is low, and if input VI is low, then output VO will be high. So this figure 1 shows a TTL inverter with an input voltage of VI and an output voltage of VO. When VI is 0 volt or grounded, the output voltage is high. With TTL devices, we can raise VI to 0.8 volt and still have a high output. If input voltage VI is 0 volt, output voltage VO is high in this inverter circuit. But if we raise input voltage from 0 up to 0.8 volt, we get output that is still high. This maximum low level input voltage is designated VIL. So worst case low input voltage VIL equal to 0.8 volt. I for input, L is low. So it is worst case low input voltage. VI is input voltage and L is for low, and worst case low input voltage is 0.8 volt. So it is the maximum voltage, maximum input voltage, which behaves as low voltage. 0 to 0.8 up to 0 from 0 up to 0.8 volt. If this is the input voltage, it behaves as low voltage. When Vi is high, 5 volt, the output of this inverter is low. Vi can decrease down to 2 volt and the output will still be low. So worst case high input volt is 2 volt and we write it as VIH. Vi input voltage and H for high. So VIH is worst case high input voltage and it is 2 volt. It means that input voltage from 2 volt to 5 volt will behave as high input voltage, and this 2 volt is the worst case. So worst case high input voltage is 2 volt. These are the worst cases for input voltages. Worst case low input voltage is 0.8 volt and worst case high input voltage is 2 volt. Now we consider worst case output voltages. These are different than these worst case input voltages. With TTL device, any voltage between 0 to 0.4 volt is low. Worst case low output voltage VOL is 0.4 volt. Because of some voltage drop across transistor Q3 and diode D1, the resistance 130 ohm, the output is less than 5 volt. In this circuit, we see that this plus 5 volt will appear as VO, as output voltage across the collector of transistor Q4, but in between this plus 5 volt battery and collector of transistor Q4, there are these three things: 130 ohm resistance, Q3 transistor and diode D1, and some voltage drop is there. So output voltage which appear across collector of Q4, it will be less than plus 5 volt. With TTL devices, a high output is between 2.4 to 3.9 volt. Worst case high output voltage is 2.4 volt. We represent it as VOH. So for output voltages, worst case low output voltage is 0.4 volt and worst case high output voltage is 2.4 volt. This table summarizes the worst case values of output voltage V and input voltage. Worst case low output voltage is 0.4 volt and high output voltage is 2.4 volt, and worst case low input voltage is 0.8 volt and worst case high input voltage is 2 volt. Compatibility. Worst case values of input and output voltages. indicate that TTL devices are compatible. These are the values of worst case high input and output voltages and low input and output voltages. And these worst case values shows that TTL devices are compatible. This means that output of a TTL device can be connected to the input of another TTL device. Figure B shows low TTL output 0 to 0.4 volt. So by compatibility we mean that we can connect output of one TTL device to the input of other TTL device. This is shown in this figure A. Output of TTL device that is on left hand side is connected to the input of other TTL device that is on right hand side of this figure. In figure B, we have VO output voltage of TTL device that is on left hand side, and this output voltage is 0 to 0.4 volt. Figure B shows low TTL output that is 0 to 0.4 volt. This is low enough to drive the second TTL device. So this range 0 to 0.4 volt will be low voltage for this second TTL device, for which this voltage behaves as input voltage. And input voltage less than 0.8 volt is low input, and input for this second TTL device is in this case 0 to 0.4 volt. So this entire range will behave as low input for this second TTL device. In figure C, high TTL output 2.4 to 3.9 volt. Output of first TTL device is high 2.4 to 3.9 volt, and it behaves as input for the second TTL device. So this high output of first TTL device that is in this range 2.4 to 3.9 volt, this also behaves as high input voltage for second TTL device, because more than 2 volt is high input voltage and it is more than 2 volt. So we see that TTL devices are compatible. We can connect output of one TTL device to the input of the other TTL device. Next characteristic is noise margin. In the worst case, there is a margin of 0.4 volt between the driver and the load in figure B and C. In figure B and C, we see that when input or output of first TTL device is between 0 to 0.4 volt, it behaves as low input for second TTL device, but for second TTL device low input is less than 0.8 volt. So if in worst case this 0.4 volt is increased up to 0.8 volt, then still it will be low input. So the noise margin is 0.4 volt. It is the difference between this 0.8 volt and 0.4 volt. Similarly, in this figure C, when output of first TTL device is high, that is in this range 2.4 to 3.9 volt, it also behaves as high input voltage to second TTL device. But for second TTL device, more than 2 volt is high input voltage. So if input is reduced, if output of first TTL device is reduced by 0.4 volt, then also it behaves as high input for the second TTL device. So noise margin is 0.4 volt either in two cases. Either output is low, output of first TTL device is low, or output of first TTL device is high. For first case, that is in figure B, it is the difference between 0.8 volt and 0.4 volt, that is equal to 0.4 volt. And in this case of figure C, this noise margin is also equal to 0.4 volt, which is the difference between this 2.4 volt and 2 volt. In the worst case, there is a margin of 0.4 volt between the driver and the load in figure B and C. Driver is TTL circuit of left hand side and load is TTL circuit of right hand side, and there is a margin of 0.4 volt between these two. This difference is called the noise margin and it represents protection against noise. The connecting wire between a TTL driver and a TTL load can pick up stray noise voltages less than 0.4 volt. Next characteristic is sourcing and sinking. When a standard TTL output is low, that is in figure B. In this figure B, output of first TTL device is low, that is in the range 0 to 0.4 volt. When a standard TTL output is low, an ammeter current of approximately 1.6 milliampere worst case exists in the direction shown. Output of first TTL device is low, then ammeter current through the ammeter of transistor Q1 of second TTL device, this will flow in this direction, in the direction of arrow of ammeter of transistor Q1 of second TTL device, and this current is 1.6 milliampere. When output of first TTL device is low, current flowing through ammeter of second TTL device is 1.6 milliampere and it flows in the direction of arrow of ammeter of transistor Q1 of second TTL device. Because output of first TTL device is low, so it is the input of second TTL device. So ammeter of second TTL device is connected to low voltage. So this ammeter, which behaves as PN diode, is in forward bias condition and 1.6 milliampere current flows in this case in the direction of arrow. An ammeter current of approximately 1.6 milliampere exists in the direction shown. The current flow between ammeter of Q1 to collector of Q4. This current flows from ammeter of transistor Q1 of second TTL device to transistor Q4 to collector of Q4. Direction of flow of this 1.6 milliampere current is from ammeter of transistor Q1 of second TTL device to collector of transistor Q4 of first TTL device as shown in this figure B. In this case, transistor Q4 is saturated. Ammeter current flows through it and it acts like a current sink. In figure B, 1.6 milliampere current flows in this direction from ammeter of Q1 to this collector of Q4, and then ammeter current through Q4 flows. It is in saturation condition and this transistor Q4 behaves as current sink because current reaches to it. When a standard TTL output is high, that is in this figure C, output of first TTL circuit is high, that is 2.4 volt to 3.9 volt, and it is connected to the input of this second TTL circuit. Now in this case, when output of this TTL device is high, then this high output is applied to the input of this second TTL device, and ammeter of Q1 is connected to high voltage. So this ammeter, which behaves as PN junction diode, is now in reverse bias condition. So in reverse bias condition, approximately zero current flows through it. So in this case, when this ammeter, which behaves as PN junction diode, is in reverse bias condition, very small current flows through it and it is in opposite direction to the direction of arrow, and this small current, which is 40 microampere, is due to minority current carriers. So when output of first TTL device is high, input of second TTL device is also high, this ammeter, which behaves as PN junction diode, is in reverse bias condition and a small current 40 microampere flows in opposite direction. A reverse ammeter current of approximately 40 microampere exists in the direction shown. The current flow from Q3 to Q1. This flow of current, that is 40 microampere current, this current is flowing from transistor Q3 of first TTL device to transistor Q1 of second TTL device. The current flow from Q3 to Q1, in this case transistor Q3 acts like a current source. Current source means from where the current is coming. So in this case, current is coming from transistor Q3 to transistor Q1. So worst case input currents are IL equal to minus 1.6 milliampere and IH equal to 40 microampere. The minus sign indicates that the current is out of the device. In the first case, when we take IL, I is current and the subscript I is for input. So II is input current and L is its worst case low value. So worst case low input current is minus 1.6 milliampere. This is the input current. Input current is for second device, that is on right hand side, and values of output are for first device, that is on left hand side. So if we consider input current, we take this second device which is on right hand side, and for this second device, worst case low input current IIL is minus 1.6 milliampere. It is minus 1.6 milliampere because this 1.6 milliampere is current is flowing out of this transistor Q1. So it is taken as negative. Similarly, in this second case of figure C, this 40 microampere current is coming into this device, so it is taken as positive and it is written as IIH, worst case high input current, that is plus 40 microampere. Plus 40 microampere means 40 microampere current is coming into this device, and minus 1.6 milliampere means 1.6 milliampere current is going out to this device. So these are the two worst case values for input currents. IL equal to minus 1.6 milliampere, IIH equal to 40 microampere. Standard loading. A TTL device can sink current or it can source current. Any 7400 device can sink up to 16 milliampere and source current up to 400 microampere. These values are 10 times the values of IIL and IIH. Worst case input currents are minus 1.6 milliampere and 40 microampere. If we multiplied by 10, then these currents are 16 milliampere and 400 microampere if we ignore the sign. So a TTL device can sink up to 16 milliampere current and it can source current up to 400 microampere. It means 16 milliampere current can come into it and 400 microampere current can goes from it. These two values are termed as worst case output current and worst case low output current is 16 milliampere and worst case high output current is minus 400 microampere. Now the negative sign is reversed. In the case of input currents, negative sign is for IIL, and now in this case of worst case output current, negative sign is for IOH. These currents are 10 times of worst case input currents, so we can connect up to 10 TTL ammeters to any TTL output as shown in following figure A and B. In figure A and B, we see that we can connect 10 TTL devices to the output of one TTL device. One TTL device which have one ammeter, because we see that if there are 10 TTL devices on right hand side, then total current is 1.6 multiplied by 10, that is 16 milliampere current, and a TTL device can sink up to 16 milliampere current. So 10 TTL devices can be connected to from the output of one TTL device having one ammeter. And this is the second case where a TTL device can source up to 400 microampere current, so it can also be connected to 10 TTL devices for which current 40 microampere can come into it. Fan out. The maximum number of TTL ammeters that can be reliably driven under worst case condition is called the fan out. So fan out for with standard TTL is 10 as shown in above figure. 10 TTL ammeters can be reliably driven under worst case. So this number 10 is known as fan out. It is the maximum number of TTL ammeters that can be reliably driven under worst case condition.